Hello everyone, and welcome to another Leetcode video. Today we're looking at the problem Construct the Minimum Bitwise Array 2, which was question 2 in Biweekly Contest 141. So the question reads that we're given an array nums consisting of n prime integers. And remember prime, this will be useful later. We want to construct an array answer of the same length n, and for each index, the bitwise OR of that element plus 1 should be equal to the original number given in that nums array. And we also want to have the minimum possible value for each of those elements in answer. And if at any point for one of those elements we cannot find any number that satisfies the condition, we just put -1 in its place. So here we have the example 2, 3, 5, and 7. And our output is -1, 1, 4, and 3. So for the first one, there's no value that satisfies this, so we put -1. For 3, we see that if we take 1 and 2, so this would be 1 and 1 plus 1, which is 2, then if we do the OR of those, we get 3. Similarly, for 5, if we do the OR of 4 and 4 plus 1, 5, I'll write that there, we see that the OR of those values is 5. But for 7, we see that if we take 3 and 3 plus 1, 4, if we OR those, we get 7. Let's look a bit closer at this example and see how we could solve it. So the first instinct you might have when looking at this problem is to just, for each number, go through all the numbers from, let's say, 1 up until that number, let's say 5 in this example, looking at this element, and we could just try all of them. So we say, let's look at 1 or 2. Does that give us our value? If not, we'll go to 2 or 3. Does that equal our value? We could do 3 or 4. So, for example, we're just really trying every single combination. This works for the first version of this question, but for the second version, this is not going to be enough because our number could potentially be up to 10 to the 9. So we would have to go through 10 to the 9 work for every single element in our array, which is going to be way too slow. So instead, we need a smarter way to figure out what this number is going to be. And for this, if you don't have good knowledge of how bits work and bit manipulation, this can definitely be a bit tricky, but I'll try to explain it and make it simple. So let's say we're looking at 5. We have 1, 0, 1. This is because this is our 4's place, this is our 2's place, this is our 1 place, right? So this means that the 4 bit is set, so this is 4, and the 1 bit is set, so we have 4 plus 1 equals 5, right? So pretty simple. But from here, how do we find the value which can, when added to the plus 1 value, or ORed rather with the plus 1 value, will give us this 5? So let's look at these bits. So if we find the rightmost group of bits and keep going until we find a 0, what we'd want to do is flip that greatest bit. So what that means is here, we're going to start here, and we say this is a 1. Okay, that looks good. Now let's go until we don't see a 1 anymore. And here we'll see that we don't see a 1, right? And what we want to do is, for this group that we found here, we want to take the leftmost one and we flip it. So this becomes 1, 0, 0. This is 4. And so if we add 4 plus 5, we do the OR value here, we see that we get 5 again. So I know I just glossed over this and it may seem like magic, but let's kind of really understand why this works. So let's look at a slightly larger number. Let's look at 23 here. So let's do the same process. We're going to go until we find the last one that's set, which is this one, and we're going to make this into a 0. So what does that look like? We have 1, 0, 0, 1, 1, which is 19, right? And why do we do this? Well, let's look what happens if we add 1 to this value. And remember, part of this is we have to find a number where when we add 1 to it and OR those values, it gives us this same 23, right? So what does adding 1 look like here? What we would get is this value here. And you see something very interesting happened with these bits here, right? And this is why we're looking for this group of ones that happened on the right. Because, for example, if we see this group of ones here, when we add 1 to it, what would happen is all these end up getting flipped. And then this next one gets set here, right? So essentially what we're doing is we're going to say, find this whole group, and then whatever is in this place here all the way on the left, we can negate this. And then what happens is that when we add 1, we're basically going to flip all these bits. So all these, as you saw, become 0, but then this becomes a 1. And that's a representation down here. So you see when we OR these, we get the same exact value, right? We get 23 again. So really what we're doing is taking advantage of the nature of binary. And we're saying that when we have this contiguous group of ones here, we know that if we add 1 to it, then all these are going to flip, and the next bit is going to get set when we add 1. So there's kind of a little trick here. If you don't really know bit manipulation very well, this is pretty hard to come by. But basically what we're doing is we're looking at this group of ones that start on the right, and whenever this ends, we're just going to flip that one. Then we can add 1 to that number, and that will be our answer. One thing that I want to point out is that the fact that we were given prime numbers is very important here, because we know primes have to be odd. And that means that this bit here, this 1 bit, will always be set. Because if this was even, this would always be a 0. But since we're dealing with prime numbers that are always odd, this has to be 1. And it guarantees that we're always going to have at least 1 bit from that right side that we're going to be able to flip. So what's the time complexity here? Well, we have to go through all of the elements. So that's going to be O of n time. But remember, we're not trying out all those 10 to the 9 combinations for each number now. We're doing it much more efficiently. So what we're really doing is for each n, we have to do 32 units of work. And this 32 represents the numbers of bits that can be set for each number. So for each number, we're going to do 32 operations, and we're going to get our answer in O of 32n time, which simplifies down to just O of n. So let's look at the code and see exactly how this is going to work. So the first thing we do is set up our answer array. This is going to be where we put numbers in and return at the end. Then we're going to go through each number. We know that num, we saw from the description, num equals 2 rather, was a special case. So if we see our number equals 2, we're just going to append -1 and continue past. Then what we're going to do is we're going to go through all of these bits that are set for the number. So we're going to go through all 32 bits. And we're going to check each bit, right? So first we're going to check the first bit, second bit, third bit. And whenever we see one that is 0, we're just going to break out. And otherwise, we're going to record the position of that bit. Then what we do is we just want to negate that last 1 bit. So what we do is we create a mask where we're going to have everything be 0 besides that position where we're going to have a 1. Then we negate it. So essentially what that means is we're going to turn all the 0s to 1s and all the 1s to 0s. So here, I'll say that again, we basically have just 1 in the position that we want to set and everything else 0s, but then when we negate it, it flips. So we have that 1, 0 in that position and everything else being 1s. Then what we do is we just append the end of those two, our original number, and the mask to our answer. And then we return at the end. So let's submit and make sure that it works. And it does work. Well, hopefully that was helpful. If you enjoyed the video, please like and subscribe, and thank you for watching.